Okay, everyone, I think we'll get started now. Okay. Hello, everyone. My name is Sam. I'm a third-year computer science student, and I'll be just demonstrating how return-oriented programming works. Now, if you were here for the binary exploitation workshop that Leo did a couple of weeks back, this is kind of the logical progression from the just ret to win and shellcode binary exploitation that you'd usually be used to. It's usually when the NX bit is enabled. That essentially means when the stack is non-executable, which means you can't do shellcode, you can't do whatever. So, as a recap, you'll know from Leo's workshop, this slide here, essentially explaining how the stack works. So you have your push and your pop. Pushing usually occurs when you're calling functions and adding variables to the stack. And popping occurs when you want to use variables or you want to jump to a function such that you can actually run that function, right? It's pretty straightforward. Return-oriented programming only really uses pop. Sometimes you'll use other gadgets and stuff like that. You'll hear me say gadget a lot. Essentially what that means is a section of code that you're able to actually reference. Every bit of code, every bit of assembly language code has its own address that you'll be able to reference. And you'll be able to use that in your buffer overflows to jump to that piece of code and then return back. And essentially what you can do is you can chain that sort of thing. I've essentially explained this slide here without going to it, but return-oriented programming is the idea of chaining these gadgets in order to cause the program to do much more complex things. Gets and puts, the usual vulnerable functions, never use them in C unless, especially with user input, especially gets, that's disgusting. Usually puts can be accessed via return-oriented programming. Say for example, you put down user input, sometimes that can be vulnerable in certain cases. It's much more rare than gets. Gets is the bad actor here. And yeah, there's plenty of assembly programming here, so be prepared. This is my drawing of essentially how this very simple program on the left here works in the stack. Essentially, as the program prepares to run the one function, it pushes it onto the stack. It then pushes two onto the stack because you're essentially going in two layers of function calls. And then once the program actually wants to run two in the first place, it will pop it from the stack. It'll jump to that function, and then it will run whatever is in said function, okay? Once it returns, that return essentially prepares it to jump back to where it jumped from. So you're essentially jumping to and from these functions in order to run what you have inside them. Now, if we can control what goes in the stack, you can do very interesting things. And this is where ROP gadgets come in. So ROP gadgets are essentially the snippets of assembly code that I mentioned earlier that you can use to overflow buffers in order to do those complex things I talked about. They can be found all over a program. Usually you want to pair them with a return, as you can see. Essentially what that'll do is it will return you back to where you last called. So let's say you overflow a buffer and then you overflow the return address with one of these gadgets, right? You're essentially running one of these bits of code, assembly code, and then you're returning back to where you jumped from, and then continuing on with what you've just placed in the stack. One useful command in order to find these gadgets is wrapper. You just place in split there, you can see is in that command I've got. It's essentially the binary. Split is what I'm going to be demoing. It's from ROP Emporium. So I encourage you guys to look at that website if you want to understand how return-oriented programming works with binaries. And then you just search the gadget that you specifically want. If you don't want to, you don't have to search either. You can just wrapper the whole binary. But if it's a large file, you probably wouldn't want to do that because it will be massive. You can do this with Radare 2 as well. -R just gets you whatever gadget you want, so long as you search for said gadget. I got a little note there and I don't remember placing that. Yeah, so when you pop a register, so ESP, ESI, EDI, ECX, they're all 32-bit registers. And when you pop a register, what you're doing is you're taking from the top of the stack and you're placing that in said register, okay? And that's gonna pop the stack and do that. Then you'll return back to what's at the top of the stack, which is whatever is this next ROP gadget that you might have chained, okay? Again, if we go back to this here, it's similar to these functions, right? I'm jumping to 2, and then I'm popping 2 and jumping to 1 once 2 is finished. Next one. Right, okay, so that is essentially, funnily enough, all the basics of ROP condensed into about 10 minutes. I'm going to be demoing it now. Sorry for who just walked in there. I've just gone over basically all of ROP and now I'm going to be demoing it without you knowing. But essentially, first thing you want to do, as with any buffer overflow, is determine the offset of said overflow. And this is where the buffer is going to overflow the stack pointer. I'm going to use, if I can share a new screen here now. Clear that, that's a spoiler. Same with all of these. So it's split. Okay, so essentially what I want to do first is whatever this slide just said. Determine the offset, that's right. So we want to use, do I have it? Yep. We want to use GDB for determining the offset, okay? So GDB is very useful for creating patterns. You might have heard of cyclic from when Leo did his workshop. Essentially what that is a non-repeatable pattern. So GDB is able to find immediately a offset of whatever register has just been overflowed. So we're gonna go ahead and GDB split, which is one of the ROP Emporium challenges. So if you guys want to follow along, download that, it's ropemporium.com. So first off, pattern create if you're on PETA. If not, it's cyclic space and then the size. So I'm going to go 150. Now, you're not given the source code for split. You have to find all of these gadgets yourself. So we create this pattern and then we just grab it, if I can grab it. Run the binary. So you can see here, I've got a 64-bit binary. And it's a little bit difficult, more difficult than 32-bit, and I will explain how 32-bit works in a moment. But for now, I'll do 64-bit if you guys want to follow along. Put that in. It's going to go segfault. And it's going to be like, ooh, you just overflowed a bunch of my registers, and I have no idea what you're doing. You can do pattern search to find certain points of offsets. So you can see the stack pointer in 64-bit is at 40. It should be the exact same in 32-bit. So you don't have to really worry about that. Now I'm going to quit out of GDB and we're going to go to the next step. Yep, you can see that, fantastic. So we're going to search the strings to see if cat flag.txt is in there. Now, if you all know how to use Linux, you'll know that cat flag.txt is just going to display the flag, right? And conveniently, there is a bin cat flag.txt string in this binary. Later on with ROP, you're able to use gadgets to actually write bin cat into the binary itself, into its statically linked variables section. So, but that's a bit complicated for today. We're just going to go over this more simple ROP program. So we're just going to go over strings. We're going to go strings, and then we're going to go split. Scroll up a little bit, you'll see all like the different sections of the program with the variable name for useful string, but you'll also actually see the string itself right there. So we know it's in there. Fantastic. Now we need to actually find the address of that string. We need to actually use that with a system call of some kind. So I'm going to go on to the next step, and that is, find where that string is stored, and then also finding where a call, if there's a call to system. If you ever come across a problem or program like this that you want to exploit in a CTF, not in real life, thank you very much, you'll want to check to see if system is in there. If it's in there, then it is going to be interesting. So we can first use this rabin2-z split. That'll get you all of, hopefully, the useful strings that the developer themselves put in the program. Sometimes it doesn't, but in this case, rabin2-z split gives us a couple of these, and we can see the address to flag.txt. Yep, I can make the text bigger. Oh, I actually don't know how to do that. Is it a hotkey? Command, Control-Shift+, fantastic. Yep. Can everyone see that? Yes, no, yep, great, okay. Okay, so you can see here we've got the string that we want to find and a couple of addresses. So P address, I'm going to be brutally honest with you all, not sure what that is. V address is the address you want to look at. So you want to grab that, and now we're going to start on the actual payload. So create a file. I use nano, shush. Just call it solution. We're going to use Pwn tools. I don't know if we all got Pwn tools. Hopefully we did during your workshop, Leo. Did we end up doing that? Yeah, okay. You want to grab Pwn tools if you don't have it. It's just PWN tools. And from that, I'm just going to import everything. Yes, it is Pwn. Okay, now you want to grab the elf. That will be equal to split. We're able to use that, and we're able to use this to essentially send and receive different parts of the binary. We'll be able to do P for process is equal to that process. Now this is the important part. This is where we create the payload. So we first want to overflow the buffer with 40 bytes. Okay, so we've now gone and overflowed the buffer. Next, we want to, if I can, oh, okay, yeah, this is actually, this is a good point here. 32-bit and 64-bit addresses are slightly different in the way that, well, system themselves, or the syscall itself uses them. You'll have, syscall itself needs to go into the EAX register, which usually is right after your offset. And then right after that is EBX, but you'll need a bit of padding before you get to EBX because there's a register there that is in between them. So system address, then 4 bytes, and then the print flag command at the end of it. This is our payload. For 64-bit, however, and this is why I went over ROP gadgets, we want to end up popping the flag, the print flag command, the string that we got, into the RDI, right? Because you can see there, the first argument to syscall for 64-bit is the RDI register. So we want to pop that in, then call system. Now, to do that, we need to find the pop RDI gadget. So we're going to just save this and move out. We're going to use wrapper -f split search, there we go. And then we want to do pop RDI, and we want to make sure we have a ret after that, okay? If you don't have a return after that, it's not going to work. You want to return back to your chained, your ROP chain. There we go. Thankfully, there is a singular instance in this binary where pop RDI exists. I wonder why. Control-Shift-C, back here. Pro Tools has a really nice way of packing hex integers into byte strings, and that is with, oh, I'm typing the wrong area because nano. P64 for 64 bits, and as you can probably guess, P32 for 32-bit addresses. You can quite literally just copy the address into there and you're done, right? That's all. So that's the pop RDI that we need. Now, if I remember correctly, we now need the actual print flag command. Yeah, that's what we just did. Yeah, so now we need the print flag. I'm going to keep that there for my reference. And we found it here. So we're going to grab that, Control-Shift-C, go back into that file. I'm going to do another little P64 of that. Last thing we need is system. Now, system we can find quite easily, actually, with GDB. There's a command in GDB called info. And we can just do info function system. Should give us the address to system right there. If we've done this correctly, go back into it here, we'll be able to send the payload to the binary through p.sendLine. Make sure you use sendLine and not send. This is a problem that occurred during Leo's workshop when I was helping some people. They used send. Send doesn't include the enter press, the new line character that occurs when you press enter. You need that, otherwise it's not actually going to send the line in the first place. It's just going to keep it there and then the program will do nothing. Send line, you just put in the payload. After that, we want to print everything that we receive because we're essentially catting flag.txt, and what that'll do is it'll cat it onto our terminal. Problem is though, is because we're using Python with Pro Tools, we actually need to make sure we print that. p.receive all. Okay. This should be fine. And once we run this, you should see a bunch of stuff that we received and hopefully a flag. And that's pretty much essentially return-oriented programming. There is a lot more complicated return-oriented programming that you can do. You can chain many more gadgets, not just the pop RDI gadget that I showed you. And usually what you're doing is you chain functions with their arguments. You make sure the registers are correct each time you do that. And so long as you have all the gadgets you need, you can do quite a large exploit. Yeah, that's basically it. One thing I would like to point out is at the beginning, I said NX bit enabled. You can check that through checksec. Checks the security of, I don't have it. That's fantastic. Yikes, that's going to take a while. While that's doing that, I'll just show you. This is what happens through checksec. This is exactly what it prints. Usually if it says NX enabled, you won't be able to do any shellcode because non-executable stack. Anyway, that's it. Thank you guys for listening to that. If you need anything, make sure you ask. This is a very difficult topic. It goes much further than a simple rent to win. And especially our challenges currently on the CTF. You'll have an easy time with the first two. Third one, you require quite a few gadgets. So again, if you need help, definitely ask me, Leo, or any of the committee members. Thank you. No, I'm just demoing it like that. Like, yeah, I have everything set to go. Yeah. But there we go. Okay. Alrighty. While you all eat pizza, I'm just gonna stumble my way through a challenge that me and Leo were looking at a couple of days ago, actually. It's called Search Engine. It's not on our CTF platform. I think it was planning to. I don't know where. I mean, if people are interested in it, yeah, I'm about to just kind of show my process and how I would attempt this sort of a challenge. So you can see I've run the program here, and we're allowed to take in some user input, and it just keeps replying, "Did you mean shellcode?" ? And that's pretty much all the program does. Whoopsie daisies. Let me just exit that. How do I get rid of my? There we go. So if I zoom in, I cannot zoom in because it is Vim. Yeah. Don't worry about it, it's fine. I got it. You'll see how the program runs here. We've got the main function, which prints out all of that garbage at the top. And then like a poor program, it uses a while loop to just run search constantly. But search is the vulnerable point here. We can see a buffer of size 128, and we can see a gets function call to that buffer. Seems to be vulnerable, right? We've got gets, we've got buffer, we've got everything really that we need. I'm going to check sec this. Hopefully it downloaded in the time. It's actually called challenge, not search engine. Yeah, I didn't. Fantastic. So I'm pretty sure the NX bit is disabled in this one. So you could do shellcode. I don't think I ended up doing that. If I take a look at the Discord and what we were talking about, yeah. So you guys, you can't see the Discord, fantastic. The main other thing that you can see in this program is not that. If I zoom in, there we go. A little weird function called ASM. Now, I don't entirely understand what this function does either. So you're on the same page as me when it comes to that. What I understand from this, though, is that it's actually inserting assembly language into the code manually. That's pretty much all I know, but it probably should be used here. I assume if this has been inserted manually and, if this is a challenge, then you can assume that we need to somehow use this. So if I, again, stumbling through this, you're gonna have to bear with me. Let's first attempt to GDB challenge. No debugging symbols found, fantastic. But we should be able to just disassemble main for now. Take a look what happens. Nothing really there. We'll disassemble search. Yeah, so let's just do a little pattern. Pattern create. I can't remember how big the buffer was. I think it was about, I don't have the cat there. I'm gonna just do 200 because I know it wasn't bigger than that. Gonna run the binary, paste that in, segfault, right? Because we've got that gets and buffer. It's gonna come up with a segfault no matter what if you end up overflowing a buffer. We can see this is a 32-bit program because we've got E registers rather than R registers. And we can see the instruction pointer is pointing to this specific point in the string now. If we do pattern search, we can find out where that is. So we've got ESP, EVP, things like that. I think the one we want to focus on is probably ESP. Let's see. We also want to find out where that ASM string was, the ASM string, because we should be able to run the assembly code that they've put in there manually. It will be somewhere in there. My sharing is paused for some reason. Let me resume the share. There we go. Oh yeah, that's why. So I'm going to attempt to find that. We should be able to find it in this for the info, x-s. This essentially allows you to examine the stack and then GMP or GMP or even like ASM, something along those lines, or maybe we can do info function ASM. Don't think that's what we're looking for. So instead, what I'm going to pull up is Gydra. Now, if you did Leo's workshop, or Omri's workshop, sorry, yep. Last week, you'll have Ghidra. So you understand a bit about how this is going to go. We're going to put challenge. Oh, we don't have an active project. Whoopsies. Just create a new project. Lol. Finish. Import the challenge. And see if we can find where this is located. Because it's a function call, it's going to be a little more difficult. It's a little different to a string or anything like that. Because we want to be able to actually find it specifically in the assembly code. Ropper, good idea. So we can do -f, we can do challenge, -- search, and then we can go, what was it? GMP, jump ESP. And we could just search for that. Right, yeah, there you go. There's a jump ESP right there. There's no ret though here, right? That's the important part of this challenge, is that there's no return value from this jump ESP. And we'll see in a moment why that's the case. If you did check sec, you'd probably notice that the NX bit is either disabled or enabled. I actually don't know what it is because I don't have check sec. I might spend the time now just to install it. That's going to take forever, but that's fine because, oh yeah, it's because I'm on Monash internet. Let me just pull up my data for a second. No one can see that, fantastic. Okay, that should be a bit better now. Might not have given it time. Yep, there you go. Okay. Cool. If we try check sec challenge, no option selected. Right. Okay. Probably. Yeah, okay. It might be a path issue then. You're right. If I do ls -m check sec. Yeah. Usually check sec would just come with Kali. I don't know why mine doesn't. So I do know where it is though, so I'm just gonna pretend that I was able to find it through Ghidra. Actually, no, we can just keep on checking through Ghidra because I know where it is if we just keep going and finding. I'm just looking through it. We can go through functions and stuff like that. Frame dummy, things like that. But really, that jump ESP, we know where it is, so we can probably attempt to use that in some way. Nano, we'll do solder pi again. And is equal to, nope. You know how big our buffer is from earlier, but we might have to do it again because I don't think I kept it. Never mind, I did. About 144 or 168, depending on what we want to do here. Looks like we want to do overflow the EIP though, so we're going to try out 144 for now. 144 plus P32 of this. That. Kind of want to see what happens if we just run that. Take a look at how the stack might go. So I'm actually going to enter GDB. I'm going to Python dash, I think you can pipe things like that. And another one and then brackets. Python dash C. So we want to print, I'm assuming, with this command, Leo. I assume that's what we want to do. And then, yeah, and then we should be able to just go A times whatever it was, 144. Plus, and then I'm just going to do a, we want byte. I'm just going to manually write this out next to here. So we want /x 82 /x 91 /x 04 /x 08. Okay. You might notice that that's backwards. That's because sorry, mind went blank for a second there. That's because the program actually reads the stack from the opposite way. I don't think this is going to work like that. I need these. Hopefully that does something. Yeah, there we go. Okay. Okay, so we actually overflowed the EIP with A's, so it was a bit large. It's 140. Nope. yeah, of course, I need to actually. Strange. There we go. Yeah, it is 144 in this ESP. Right. I have a feeling we are running the code. Essentially what jump ESP is doing is it's returning back to a portion of the stack that you have. So in this scenario, I think one of the checksec bits is enabled such that you can't overwrite the return pointer properly in order to then run shellcode of some description. Mm-hmm. Yeah. Overwrite the return address of the jump ESP gadget, then shellcode should execute provided NX bit is disabled. Yeah, so NX is going to be disabled in this. Ah, that's the problem. Okay. So the cool thing about this challenge in particular is that it uses ASLR. And essentially what that does is it makes using shellcode really tricky because the addresses are randomized. And so you aren't able to jump to a NOP sled quite as easy. Let's have a look. Yeah, okay. Yeah, I might just grab that shellcode actually. Because I can't be bothered finding my own. I'm not going to do it there. Do you guys see that? No, good, okay. MonSec. Whoever made this challenge for the beginner CTF, shame on you. Tut. I haven't written in there. No, people aren't following. Yeah, right. Return address, shellcode. Fair enough, all right. I'm just going to wrap up here. Essentially what's happening is the stack isn't being cleared. So if you have ASLR on, the stack is going to be much harder to jump to. So what this program is able to do is if you have a jump ESP, which isn't usually in a binary, you're able to actually jump into the stack directly to execute your shellcode. And that means that it doesn't matter whether ASLR is on or off, because the randomization won't matter. You'll be able to just jump directly to the stack. That's pretty much it. Again, just stumbling through it. See if I can actually get it to work though, but I won't be talking much more. You off there? Okay. Yeah, I'll finish it up now. Nice to meet you too. Yeah. Cool. That's about it from me as well, guys. Again, any questions, definitely ask. But other than that, I think our workshop is over. So thank you for coming, everyone.